we have misunderstood the universe. Those are not my words. Those are the words of Adam Rees, a Nobel Prize-winning physicist at Johns Hopkins University. A man who has dedicated his entire career to measuring the speed at which the cosmos is flying apart, galaxy by galaxy, megaparsec by megaparsec, across billions of light-years of emptiness. And he is not being dramatic. He is not reaching for a headline. He is sitting with his data collected by the most powerful space telescope ever built, and telling us plainly, carefully, with the restraint of a scientist who weighs every word, something in our model of reality does not add up. Think about what it takes to say that. This is not a fringe researcher lobbing provocations from the margins. This is one of the architects of modern cosmology, a man who helped discover that the expansion of the universe is accelerating, a discovery so startling it earned a Nobel Prize in 2011. And now he's looking at the universe again, through better eyes, with better instruments, and he's telling us the model is cracking. For nearly a century, cosmology has rested on a single, elegant framework. We call it the lambda-CDM model, or more commonly, the Standard Model of cosmology. It is a set of equations and assumptions describing everything from the first fraction of a second after the Big Bang, when the universe was smaller than an atom and hotter than anything we can imagine, all the way to the present day. It has worked beautifully for decades. It predicted the existence of the cosmic microwave background before we detected it. It explained why there are roughly 3 hydrogen atoms for every helium atom in the universe. It described with breathtaking precision the large-scale structure of the cosmos, the way galaxies cluster into filaments and voids that stretch hundreds of millions of light-years across. It accounted for observations so varied, so independent of each other, that its success seemed almost suspicious, almost like the universe had been built to fit the model. And then the James Webb Space Telescope turned on. What Webb found did not confirm our understanding. It complicated it. In some cases, it flatly contradicted it. And the deeper we've looked with this extraordinary machine, the wider the cracks have become. Not small cracks. Not the kind of cracks you patch with better calibration or a slight tweak to a constant. The kind of cracks that make you wonder whether the whole foundation needs re-examining. Do you find this kind of thing fascinating? Drop a comment below. I want to know what aspect of cosmology keeps you up at night. And if you haven't subscribed yet, hit that button now. We're just getting started. The number at the center of everything. The trouble starts with a single number. It is called the Hubble constant, and it measures the rate at which the universe is expanding right now. Not in the early universe, not in some theoretical future. Right now, at this moment, as you watch this video, as light travels toward your eyes, as the galaxies beyond our local group continue their inexorable retreat into the darkness. You would think a number like that would be straightforward to pin down. One universe, same physics everywhere, 2 independent measuring methods, one answer. That is how science is supposed to work. It didn't. And this isn't the first time this particular number has caused trouble. The Hubble constant has been a battleground since the 1920s, when Edwin Hubble himself first calculated it from observations of galaxies he could barely resolve through the best telescopes of his era. His original estimate was so catastrophically far off that it made the universe appear younger than the oldest rocks on Earth. The universe, apparently, was younger than its own planets. That made no sense. For decades after Hubble's first measurement, 2 camps of astronomers fought with genuine bitterness over the true value. Alan Sandage, who had been trained by Hubble personally, argued the constant was close to 50 kilometers per second per megaparsec. Gérard de Vaucouleurs and his allies insisted it was closer to 100. Double. The disagreement wasn't academic. It changed the age of the universe by billions of years. It determined whether there was enough time for galaxies to form, for stars to live and die, for the heavy elements inside you to have been forged and scattered across space. The two camps barely spoke to each other at conferences. The tension was that personal. By the early 2000s, the war appeared to be over. The Hubble Space Telescope Key Project, led by Wendy Friedman, published a comprehensive measurement, approximately 72 kilometers per second per megaparsec, with an uncertainty small enough that both camps had to concede. The fight was resolved. The number was known. Science had prevailed, except the victory was temporary. As instruments got more precise, a new split emerged, smaller than the old one, far more stubborn. And unlike the old disagreement, which was fundamentally about the quality of the data, this new one stubbornly persists even when the data is excellent. Two methods, two universes. There are two primary ways to measure how fast the universe is expanding today, and they represent philosophically different approaches to understanding the cosmos. The first method looks backward, way backward. The European Space Agency's Planck satellite spent 4.5 years, from 2009 to 2013, scanning the entire sky with extraordinary sensitivity, mapping the cosmic microwave background. The faint afterglow of radiation released when the universe was approximately 380,000 years old. At that point, the cosmos had cooled just enough for electrons and protons to combine into neutral hydrogen atoms, allowing photons of light to travel freely for the first time. Those photons have been traveling ever since. They bathe the entire universe in a whisper of microwave radiation, carrying encoded within them a snapshot of the infant cosmos. From that ancient map, physicists extracted the conditions of the early universe, its temperature, its density, the ratio of normal matter to dark matter to radiation, and fed them into the standard model. They ran the equations forward across nearly 14 billion years of expansion and asked, given everything we know about how the universe evolves, how fast should it be expanding right now? The answer was 67.4 kilometers per second per megaparsec. A tight number, a precise number, a confidence level so high that cosmologists considered it essentially settled. For every 3.26 million light-years you look outward, galaxies should be receding from us at 67.4 kilometers per second faster. The second method is more direct, more grounded. Instead of modeling the past and projecting forward, it measures the present. Adam Rees and his team, working under the name SHOES, supernovae H-O for the equation of state, use a technique known as the cosmic distance ladder. It is one of the most carefully constructed chains of reasoning in all of science. The first rung of the ladder, Cepheid variable stars. These are pulsating stars whose brightness fluctuates at a rate directly tied to their intrinsic luminosity. The period of the pulsation reveals the true brightness of the star. Compare that true brightness to how bright the star appears from Earth, and you can calculate the distance with high precision. This relationship was discovered by Henrietta Swan Leavitt in 1908, one of the most important discoveries in the history of astronomy, made by a woman who was paid 25 cents an hour to analyze photographic plates and who received no Nobel Prize because she had died by the time the committee came looking. From Cepheids, the ladder steps outward to galaxies that contain both Cepheid variables and a specific type of stellar explosion, Type 1A supernovae. These supernovae are cosmological rulers. When a white dwarf star accretes enough mass from a companion to trigger a thermonuclear explosion, it always blows apart with approximately the same peak brightness. Not exactly the same, there are subtle variations that astronomers know how to correct for, but close enough that once you've calibrated them using Cepheids in the same galaxy, you can use them to measure distances across hundreds of millions of light-years. They are bright enough to see across a significant fraction of the observable universe, and uniform enough to trust. Combine the distances with the recession velocities of those distant galaxies, and you get the Hubble constant, Rees's team ran this process meticulously, cross-checking at every step, and arrived at 73.04 kilometers per second per megaparsec. Not 67, 73. A gap of roughly 8 to 9% between two independent measurements of the same fundamental constant of nature. That might sound like a rounding error. It is not. In a field where measurements are routinely precise to within 1%, a gap of 8 or 9% between two independent methods is enormous. It's the kind of discrepancy that keeps physicists awake. Not because it's embarrassing, because it's interesting, because discrepancies like this are how new physics gets found. What does an 8% difference actually mean? Think about it this way. If the universe is expanding at 73 instead of 67, then it has been expanding faster than we thought for its entire history. That compresses the timeline. The universe appears younger, perhaps by more than 1 billion years. It changes the distances to galaxy clusters. It alters the rate at which galaxies are separating from each other, which affects our predictions for the fate of the universe. It changes the inferred properties of dark energy, the mysterious force that has been accelerating the expansion since the universe was roughly half its current age. And dark energy makes up 68% of everything that exists. Misunderstand dark energy, and you misunderstand the dominant ingredient of reality. You are not just adjusting a dial on a dashboard. You are redrawing the entire history of everything that has ever existed. Why Webb should have fixed this, and didn't. For years, the most popular explanation for the Hubble tension was a relatively mundane one: a calibration error. Specifically, a phenomenon called stellar crowding. Cepheid variable stars tend to live in the dense, dusty disks of younger, actively star-forming galaxies, exactly the kind of environment where stars are packed closely together. When the Hubble Space Telescope looked at these stars, its cameras sometimes blended the light from nearby, unrelated stars with the light from the Cepheid itself, making it appear brighter than it truly was. If a Cepheid looks artificially bright, you calculate a shorter distance than the true one. Shorter distances feed into a higher Hubble constant. If you could clean up that blending, if you could resolve individual stars with enough precision to separate their light, the argument went, the tension would relax. So Adam Rees did something audacious. He pointed the James Webb Space Telescope at the same Cepheid variables. Hubble had been studying for decades. The James Webb Space Telescope is not just an upgrade over Hubble. It is a different kind of instrument entirely. Webb orbits the Sun at the second Lagrange point, 1.5 million kilometers from Earth, far enough from our planet's heat and reflected sunlight to maintain the cryogenic temperatures its infrared detectors require. Its primary mirror is 6.5 meters across, more than twice the diameter of Hubble's, composed of 18 gold-plated beryllium hexagonal segments that unfolded in space with the precision of a Swiss watch after launch. It sees primarily in infrared light, which cuts through dust the way X-rays cut through skin, revealing objects hidden from optical telescopes in clouds of obscuring gas. If any telescope in human history could settle the Hubble tension, it was this one. The expectation among many physicists was cautiously optimistic. Webb would peer into those crowded, dusty galactic disks with its superior resolution, separate the Cepheids from their neighbors, correct the blending error, and the Hubble constant would drop back towards 67. Some researchers were already preparing papers. The crisis, many felt, was about to be solved the quiet, anticlimactic way that most crises in science are solved, through better data. That is not what happened. In early 2024, the SHOES team published a landmark paper in the astrophysical journal Letters. They had used Webb to examine Cepheid variables across 5 host galaxies, extending their measurements out to NGC 5468, a galaxy roughly 130 million light-years from Earth. 1,000 Cepheids, 8 Type 1, a supernovae. The full span of Hubble's Cepheid dataset, re-observed with Webb's sharper eyes, in infrared, cutting through the dust, separating the stars. The Cepheids looked the same. The distances held. The blending correction turned out to be real. Webb did find some crowding, but accounting for it moved the Hubble constant by barely a fraction of a percent. The expansion rate stayed at 73. The conclusion, stated plainly in their paper, was unequivocal. Measurement error could be ruled out with very high confidence. The Hubble tension is not a telescope problem. It is not a calibration problem. It is not a mistake. It is a real discrepancy between two accurate measurements of the same universe. Rees put it with the quiet devastation of someone who had hoped for a different answer. With the errors eliminated, what remains is the possibility that we have misunderstood the universe. At a conference at the Kavli Institute for Theoretical Physics in California, years before Webb launched, Rees had asked David Gross, a Nobel laureate in particle physics, whether the field should be calling this a problem. Gross corrected him. "Don't call it a tension," Gross said. "Don't even call it a problem. Call it a crisis." By December 2024, the crisis had only deepened. Rees's team published their largest Webb study yet, compiled from the telescope's first 2 full years of operation. They had cross-checked their Cepheid measurements against 2 independent distance indicators: carbon stars, which are red giant stars with a characteristic brightness that can be measured across millions of light years, and a technique called the tip of the red giant branch, which uses the predictable maximum brightness that red giant stars reach just before they undergo a helium flash. 3 independent methods, 3 independent rungs on the distance ladder. All 3 agreed with Hubble's original Cepheid measurements. All 3 pointed to a universe expanding at 73. The standard model predicts 67. The universe insists on 73. The dissenters and the no man's land. Not everyone believes the tension is real, and this is where the story gets genuinely complicated in a way that reflects how science actually works, as opposed to how textbooks describe it. Wendy Friedman, the same astronomer who led the Hubble Key project that settled the old Hubble wars in the early 2000s, has spent years building a competing distance ladder, one that relies less heavily on Cepheid variables, which she worries may have systematic errors that Webb has not fully eliminated. Her team uses a broader toolkit: red giant stars, Cepheids, and a class of evolved stars called JAGB stars, found in older, quieter regions of galaxies where crowding and dust are less severe. In August 2024, Friedman's team published their own Webb analysis. It was not a clean result. Her 3 distance methods gave different answers. The red giant measurements and the JAGB method both landed between 68 and 70, consistent with the Planck prediction and the standard model. Her Cepheid measurement came in around 72, closer to Rees, but with larger uncertainties. Her combined result, attempting to average across all 3, was approximately 70 kilometers per second per megaparsec, sitting in a kind of no man's land, not quite confirming the tension, not quite resolving it. Saul Perlmutter, who shared the 2011 Nobel Prize with Rees for discovering the accelerating expansion of the universe, reviewed Friedman's data before publication and made an observation that reframed the problem. The issue, he noted, might not be between the early and late universe measurements at all. There appears to be a tension within the star-based measurements themselves. Different types of stars in the local universe, measured with the same telescope, are giving different answers. That is a different kind of problem. It means the distance ladder, the tool astronomers have relied on for a century to map the nearby cosmos, may have unresolved issues at its foundation. Rees pushed back. He argued that Friedman's analysis had relied on a small and potentially non-representative sample of Type 1a supernovae, which could bias the Hubble constant estimate downward. The disagreement between the two teams has become one of the most intensely watched rivalries in modern astrophysics. Two brilliant groups, two careful methodologies, two conclusions that don't quite agree. What's your take? Do you think this is a measurement problem waiting to be solved, or a genuine crack in the standard model? Let me know in the comments. This is exactly the kind of debate that science needs. The crisis within the crisis. What could be hiding in the physics? If the Hubble tension is real, and the weight of current evidence strongly suggests it is, then something is missing from our picture of cosmic history. The standard model, fed with observations of the early universe, predicts a certain expansion rate today. The universe delivers a higher one. Somewhere in those 13.8 billion years between the Big Bang and now, something happened that the standard model doesn't account for. The most discussed candidate goes by the name of early dark energy. The idea is striking in its elegance. What if there was a brief burst of additional energy in the very early universe, in the first few 100,000 years after the Big Bang, that drove a period of extra expansion and then vanished? Not the dark energy we observe today, which is a constant property of space itself. A different kind, temporary, violent, gone before the universe was 1,000,000 years old. If early dark energy existed, it would have subtly altered the conditions in the early universe in just the right way to shift the Planck satellite's predictions upward, closer to 73, without breaking the other remarkable things the standard model gets right. Mark Kamiankowski, a cosmologist at Johns Hopkins, who has been one of the primary architects of this idea, has compared it to the universe receiving an unexpected kick right after it was born. A nudge, a push, something that left its fingerprints not in the cosmic microwave background itself, but in the mismatch between what the background predicts and what we actually measure. Nobody has detected early dark energy. It remains a hypothesis, a tantalizing one, supported by some data, contradicted by other data, vigorously debated at every major cosmology conference. But it is one of the few ideas on the table that could explain the Hubble tension without requiring us to throw out the standard model entirely. Other proposals are more radical. Some physicists have suggested that dark energy is not actually constant, that it has evolved over the history of the universe, stronger at some epochs than others, changing the expansion history in ways that create the tension we observe. In April 2024, preliminary results from the Dark Energy Spectroscopic Instrument, DESI, which mapped the positions of tens of millions of galaxies to trace the history of cosmic expansion, suggested that dark energy may indeed be changing over time. Not definitively, not with enough statistical confidence to declare a discovery, but enough to make the physics community take notice. If dark energy evolves, the standard model needs to be replaced with something more sophisticated. Others have proposed modifications to general relativity itself, the theory that governs how gravity works on cosmic scales. Still others have suggested that the universe is not as uniform as we've assumed, that we live in a region that is slightly less dense than average, creating a local bubble in which the expansion rate is genuinely faster than the cosmic mean. This idea, sometimes called the Hubble bubble or void hypothesis, is an uncomfortable one. It would mean our measurements are locally accurate, but cosmically unrepresentative. It would reintroduce a kind of cosmic special pleading that physicists have always tried to avoid. None of these ideas is proven. None has yet replaced the standard model. But the fact that they are being seriously discussed by serious people tells you something about the depth of the current crisis. Galaxies that shouldn't exist. The Hubble tension would be enough on its own to shake cosmology. Webb delivered a second blow. Almost as soon as the telescope began observing the deep universe, pointing toward the most distant, most ancient light it could detect, it found galaxies that had no business being there. Not the small, dim, barely formed proto-galaxies that the standard model predicted at those distances. Massive ones. Fully assembled, star-rich galaxies, seen as they appeared just 500 to 700 million years after the Big Bang. Galaxies that, by any reasonable extrapolation from the models, should not have had enough time to build themselves. Consider what it takes to build a galaxy. You start with a diffuse cloud of hydrogen and helium, the primordial gas left over from the Big Bang. That gas needs to collapse under gravity into denser regions, form the first stars. Let those stars live and die and explode, seeding the gas with heavier elements, allowing the next generation of stars to form, letting the gravity of dark matter halos pull gas inward, and doing all of this repeatedly across hundreds of millions or billions of years. The Milky Way, with its roughly 200 billion stars, took essentially the entire history of the universe to build. And it's still not done. Yet Webb was finding galaxies comparable in mass to our own, some potentially even larger, when the universe was less than 5% of its current age. Mike Boylan Colchin, an astronomer at the University of Texas at Austin, ran the numbers in a study published in Nature Astronomy. He showed that 6 of the earliest and most massive galaxy candidates observed by Webb pushed right up against the absolute theoretical limit of what the standard model allows. In a normal universe, the conversion of gas into stars proceeds at roughly 10% efficiency. 90% of the available gas never makes it into a star. It's too hot. It gets blown out by radiation from existing stars and supernovae. It drifts away. It falls into black holes without forming anything. These galaxies appeared to be running at 100% efficiency. Every available atom of gas turned into a star, with nothing wasted, nothing lost. Physics doesn't work that way, not in any model anyone had ever built. The initial reaction in the scientific community was, to use the language of several papers published at the time, frankly alarming. If these galaxies were as massive as they appeared, then either our models of galaxy formation were deeply incomplete, or the standard model of cosmology, the lambda-CDM framework, needed fundamental revision. Subscribe now if you want to be here when we cover the next major development. New findings are coming out faster than ever, and this story is far from over. The plot twist: black holes in disguise. Then came a correction, and this is the part of the story that demonstrates something important about how science actually works, especially in the era of Webb. Katherine Chwarowski, a graduate student at the University of Texas, working with Stephen Finkelstein, one of the leading observational cosmologists studying the early universe, led a meticulous re-examination of the Webb data. What she found reframed the problem entirely. Many of the apparently overmassive galaxies were not actually as massive as they appeared. They were being fooled, or rather, we were being fooled, by their own black holes. These galaxies, which quickly acquired the nickname little red dots because of their compact appearance and reddish color in Webb's infrared cameras, hosted supermassive black holes at their centers that were voraciously consuming surrounding gas. In the early universe, when galaxies were denser and gas was more plentiful, this kind of rapid black hole growth, quasar activity, was common, and the friction from all that infalling material heated the gas to extreme temperatures. That heat radiated outward as light, enormous amounts of light, blending seamlessly from our vantage point billions of light years away with the starlight from the galaxy itself. From that distance, through Webb's cameras, a galaxy with a moderately hungry black hole at its center looks almost identical to a galaxy with 10 times more stars. The telescope sees brightness. Brightness is normally a reliable proxy for stellar mass. But in these cases, the black hole was doing the work of billions of suns, inflating the galaxy's apparent mass like someone taping a floodlight to a candle and calling it a city. Once those little red dots were removed from the sample, once the black hole-contaminated measurements were excluded, the remaining galaxies fit within the standard model's predictions. Finkelstein was direct about it. There is no crisis in terms of the standard cosmological model, he said. Not from the galaxies, at least. But the story didn't end there cleanly. It never does. Even after removing the little red dots, roughly twice as many massive early galaxies remained as the standard model's most precise simulations expected. Not enough to break the model, enough to bend it, enough to require adjustments to how we think galaxies formed and grew in the first billion years of cosmic history. Chwarovsky suggested that stars may have formed faster in the early universe than they do today, that the denser conditions shortly after the Big Bang made it harder for gas to escape during star formation, allowing the process to run at higher efficiency. A plausible explanation, but one that still requires revision to the standard picture of galaxy formation. The Big Wheel and the Chaotic Adolescence. In early 2025, Webb found something else, something that didn't fit neatly into any of these categories. A massive spiral galaxy, ancient, seen as it was within the first 2 billion years of the universe's existence, quickly nicknamed the Big Wheel by the team that discovered it at Swinburne University of Technology. Spiral galaxies are not supposed to exist that early. Spiral structure, the elegant, sweeping arms that define galaxies like the Milky Way and Andromeda, takes time to develop. It requires relatively calm, orderly growth, steady accretion of gas, stable rotation, the gradual settling of stars into circular orbits. What you expect in the young universe, when everything is colliding and merging and exploding, is chaos. Clumpy, irregular protogalactic blobs smashing into each other, building mass through violence. Not this, not a serene, structured spiral. Thamiya Nanayakara, one of the astronomers who discovered the Big Wheel, noted that the galaxy either assembled its mass in an unusually calm and orderly fashion, or it formed most of its stars in place, without the violent collisions and mergers that typically dominate galaxy assembly in that era. Either explanation requires adjustments to how we model early galaxy formation. Meanwhile, a separate team at Cambridge used Webb to study more than 250 galaxies from that same era and found the opposite pattern. Most of them were precisely what the standard model predicts: chaotic, turbulent, clumpy systems without coherent structure. Messy adolescents of the cosmos, not yet settled into the elegance they would eventually develop. So the early universe contained both chaotic proto-galactic blobs and at least one remarkably mature spiral galaxy, coexisting in the same epoch. That is not a contradiction the standard model handles gracefully. It suggests either that galaxy formation is more varied, more dependent on local conditions, than the simulations capture, or that there are processes at work in the early universe that we haven't adequately modeled. The shape of darkness. When galaxies look like cigars, none of this addresses what may be the deepest structural challenge Webb has revealed. A study published in Nature Astronomy in late 2025, led by Alvaro Pozo and including researchers from MIT, Harvard, and the Academia Sinica Institute of Astronomy and Astrophysics in Taipei, found something unexpected in the shapes of young galaxies. Many early galaxies observed by Webb appear elongated, stretched, not the round or flattened disk shapes the standard model predicts for young galaxies, but long cigar-like structures, what astronomers call prolate morphologies, extended along a single axis like a cosmic needle. These shapes are strikingly inconsistent with predictions from the cold dark matter model, which is not just one ingredient in the standard framework. It is the scaffolding. The cold dark matter model determines where galaxies form, how they cluster, how the large-scale structure of the universe, the cosmic web of filaments and voids, is organized on the largest scales. In the cold dark matter model, the fundamental particles of dark matter are heavy, slow-moving, and clumped together under gravity into roughly spherical halos. Galaxies form inside those halos, and their shapes are largely determined by the merger history within those halos. Elongated structures are not a natural prediction of this scenario. But those cigar shapes do match predictions from two alternative models of dark matter. Warm dark matter, in which the dark matter particles are lighter and faster moving, and fuzzy, or wave dark matter, in which dark matter is an ultralight quantum particle that behaves more like a wave than a particle on galactic scales. In both alternatives, the filaments of the large-scale structure are smoother, and gas and stars can flow along them in elongated streams rather than collapsing into compact blobs. The distinction matters more than it might seem. Cold dark matter isn't just a detail of the Standard Model. It is the reason the Standard Model makes the predictions it does about everything, from the distribution of dwarf galaxies to the way gravitational lensing warps light around massive objects. If dark matter particles are lighter or behave differently than the cold model assumes, the consequences cascade through almost every prediction cosmology makes. You cannot swap out the foundation of a building and expect the walls to remain standing. This is the conversation we should all be having. If you want to understand where physics is actually heading, not the textbook version, but the living, breathing, contested frontier, stay subscribed. New data is coming. The picture is changing, and you don't want to miss it. The S8 tension, the quieter crisis. There is a second, quieter tension that most people haven't heard about. It doesn't have the drama of the Hubble tension. It hasn't earned conference keynotes or Nobel-adjacent headlines. But physicists who study it closely consider it equally important. It is called the S8 tension, and it concerns how clumpy the universe is. Matter in the universe is not uniformly distributed. It clusters. Gravity pulls gas and dark matter together into filaments and nodes, creating the cosmic web. The Standard Model, given its description of the early universe, makes precise predictions about how much clustering there should be in the distribution of matter across space today, how pronounced those filaments and voids should be, how tightly galaxies should cluster around each other. When astronomers measure that clustering directly, through surveys of galaxy positions, through weak gravitational lensing, the way the gravity of foreground matter distorts the shapes of background galaxies, through the Sunyaev-Zeldovich effect, the way galaxy clusters leave imprints on the cosmic microwave background as photons pass through them, they consistently find slightly less clustering than the Standard Model predicts. The universe is a bit smoother than it should be, a bit less structured. Rees has called the S8 tension the little sibling of the Hubble tension, less dramatic, but persistent across multiple independent measurements using multiple independent methods from multiple independent teams. If both the Hubble tension and the S8 tension turn out to be real, and if they share a common underlying cause, they might be telling us the same thing about some missing ingredient in our physics, two cracks in the same wall, two symptoms of the same disease. Where the Standard Model stands. So where does all of this leave us? The Standard Model is not dead, not even close. Let me be clear about that, because the temptation in a video like this is to overstate the crisis for dramatic effect, and that would be dishonest. The lambda CDM model still explains the cosmic microwave background with extraordinary precision, arguably the greatest predictive achievement in the history of science. It predicted the precise ratios of hydrogen, helium, and lithium that we find in the oldest stars. It correctly described the large-scale structure of the universe, the cosmic web, before we had the surveys to map it. It accounts for the acceleration of cosmic expansion and points to the existence of dark energy. It explains why the universe looks roughly the same in every direction. No competing model can match its track record. No alternative framework comes close to fitting all the data, but it is developing fractures that weren't there a decade ago. The Hubble tension refuses to go away, and Webb has, if anything, made it more stubborn. The early universe is producing galaxies that are bigger, more structured, and stranger than our best simulations predict. The nature of dark matter, which makes up roughly 27% of everything that exists, may not be what we've been modeling for the past 25 years. And dark energy, the 68% of the universe responsible for its accelerating expansion, remains a placeholder name for something we cannot identify, cannot measure directly, and cannot explain from first principles. We named it. We quantified its effects. We have no idea what it is. Rees put it carefully and precisely in December 2024, in the way that physicists learn to speak when they want to be accurate without triggering a media panic. The discrepancy between the observed expansion rate and the predictions of the Standard Model suggests that our understanding of the universe may be incomplete. Two NASA flagship telescopes now confirm each other's findings. We have to take this problem seriously. We have to take this problem seriously. From a Nobel laureate who has spent his career being careful with his words, that is a statement worth sitting with. Instruments on the horizon. New instruments are coming, and they will either resolve these tensions or deepen them. NASA's Nancy Grace Roman Space Telescope, scheduled for launch in the next few years, will conduct wide-field infrared surveys designed specifically to map the distribution of dark energy across cosmic time. Its enormous field of view will allow it to survey hundreds of millions of galaxies, measuring their positions and shapes with the precision needed to test whether dark energy is truly constant or whether it has evolved over cosmic history. The European Space Agency's Euclid mission, which launched in 2023 and is already producing results, is mapping the geometry of the universe on scales no telescope has attempted before. Its weak lensing surveys will measure the S8 tension with unprecedented precision, either confirming it or explaining it away. Future data releases from the Gaia Space Telescope will allow astronomers to calibrate Cepheid distances using geometric parallax measurements, the most fundamental distance measurement technique available, reducing another potential source of systematic error in the cosmic distance ladder. And the Atacama Cosmology Telescope has already produced the most detailed ground-based map of the cosmic microwave background ever made, slightly nudging the Planck estimate of the Hubble constant upward, but not far enough to close the gap. Not yet. The Dark Energy Spectroscopic Instrument, operating at Kitt Peak in Arizona, is in the middle of a 5-year program to map the three-dimensional positions of more than 40 million galaxies, tracing the history of cosmic expansion with a detail that was unimaginable a decade ago. Its early results, released in 2024, already hint that dark energy may be more complex than the simple cosmological constant of the Standard Model. We are living in the most data-rich era in the history of cosmology. New measurements are arriving faster than theorists can model them. New anomalies are piling up before the old ones are explained. The picture is not converging. It is expanding, in more than one sense. The feeling at the frontier. What's remarkable about this moment in cosmology, and what I think gets lost in the breathless press releases and the alarming headlines, is that the prevailing mood among the physicists at the center of this is not panic. It is not despair. It is something closer to the feeling you get when you've been assembling a jigsaw puzzle for years, certain you had the picture right, and then you turn over a piece and find it doesn't fit anywhere in the image on the box. The puzzle isn't wrong. The image on the box might not be the whole picture. There is excitement underneath the anxiety. There is the electric feeling that something is about to change, that a new piece of physics is hiding just beyond the current instruments, just beyond the current theories, waiting to be found. Physicists have been here before, and they know what this feeling means. In the 1990s, cosmology appeared to face a fatal contradiction. Measurements of the Hubble constant were suggesting the universe was only about 8 billion years old. But astronomers were measuring the ages of the oldest stars in globular clusters, dense, ancient collections of stars orbiting the Milky Way, and finding that some of them were more than 13 billion years old. The universe couldn't be younger than the stars inside it. That made no sense by any physics anyone knew. The field was genuinely troubled. And then, in 1998, two independent teams studying Type 1a supernovae, one of them led by Adam Rees himself, the other by Saul Perlmutter, discovered that the expansion of the universe is not slowing down, as gravity should be causing it to. It is speeding up. Something is pushing everything apart, something that acts like a negative pressure built into the fabric of space itself. Dark energy. With that discovery, the contradiction evaporated. The universe is not 8 billion years old. It is 13.8 billion years old, and it has been accelerating for the last 5 billion of those years. The apparent contradiction was not a flaw in the model. It was the shadow of something enormous that nobody had seen yet. That's the thing about crises in physics. They feel like dead ends. They almost always turn out to be doors. The view from outside. If you could somehow stand outside the universe, outside time and space and causality, in whatever void surrounds the void, and watch this moment, here is what you would see. A species on a small rocky planet, orbiting an unremarkable yellow star in the outer suburbs of a mid-sized spiral galaxy, in a universe of perhaps 2 trillion galaxies. A species that has existed for the blink of a cosmic eye. A species that, a few centuries ago, did not know the Earth went around the sun, did not know other galaxies existed, did not know the universe had a beginning. That species is now, at this moment, using gold-plated mirrors deployed in deep space to argue about whether reality is expanding 9% faster than it should be, and getting genuinely, personally, passionately upset about it. That is either the most absurd thing in the universe or the most magnificent. I believe it is both, simultaneously, inseparably. This is not a failure of science. It is not a collapse of understanding. It is the opposite. This is what it looks like when a field of knowledge reaches the absolute boundary of what it knows, stares into the darkness beyond, and keeps pushing. The standard model is not broken. Our map of the cosmos is just incomplete. And the next version of that map, whenever it arrives, built from whatever physics we discover in the coming decades, is going to be stranger and more beautiful and more surprising than anything we have drawn so far. The universe is bigger than our best ideas about it. It always has been. That's not terrifying. That's the whole point. What part of this do you want to know more about? The Hubble tension? Dark energy? The formation of early galaxies? Tell me in the comments. Your questions shape what we cover next. And if you're not subscribed, now is the time. We are living through one of the most extraordinary moments in the history of science, and this channel is going to be here for every development. I hope you enjoyed the video. If you did, please hit that like button. It makes an enormous difference in helping this channel reach people who love this content but haven't found it yet. Subscribe if you haven't already and ring the notification bell so you never miss an upload. There is so much more to explore. The universe is not done surprising us, and neither are we. Thanks for watching. I'll see you in the next one.